Okay, guys, I wanted to do a quick video here for our next unit on geometry optimizations. And so I'm going to talk a little bit about potential energy surfaces to give you an idea of what I'm talking about. And then I'll go over a few key points about performing geometry optimizations and transition state calculations using Gaussian. And then in separate videos, I'll have some example calculations for you to refer to as you attempt your mini project on these topics. So something that we've already discussed is that the energy of a molecule is a function of the molecular geometry. So that is, as the atoms move around relative to one another, the energy of the molecule changes. And you can think of the energy as a map related to the molecular geometry. So you can map out the energy as a function of the molecular geometry. That's that hyperdimensional surface that is created is what we refer to as the potential energy surface. And so what the geometry optimization calculations within Gaussian do is they find so-called stationary states, or stationary points, I should say, on that potential energy surface. These can be local minimum energy structures, or if you combine these geometry optimizations with a conformational search among many local minimum energy structures, you can locate the global minimum energy of the molecule. Or if you're not interested in minimum energy states, you can find what are referred to as transition state structures. These are also called saddle points. And so what I'm going to do is highlight, using a figure from the book, what these different structures are. And so here is a two-dimensional potential energy surface, meaning that you've got two coordinates. One of them runs this way, and the other one goes back into the screen in this direction. And so this would be a very simplified version of a molecular potential energy surface. In principle, those would be the number of dimensions would be 3 times the number of atoms minus 6, or possibly 3 times n minus 5, depending on whether your molecule is nonlinear or linear. And so when I say a hyperdimensional surface, I mean just that. It has many more dimensions than you can visualize using a simple picture. But anyway, in this cartoon, we've got two coordinates. And so this surface that you see here, this represents the energy of the molecule as a function of these two coordinates. And you can see that it changes as you go to different points in this two-dimensional space. And you see that there's a number of minima in the energy. Okay, so these energy here, these points right here, these are called the local minima. Okay, they're bottom points on the potential energy surface, but they're not the lowest possible minimum. Here, which is at much lower energy, this is what we would call the global minimum, the one that has the geometry that has the lowest possible energy for that molecule. And then you see, as you move away from these minimum energy structures, the energy goes up, whether you go this way or go that way or this way or that way. You also see here, there's local maxima as well. Those are usually less interesting for thinking about chemistry, although they may be of some interest. More interesting for chemistry are these so-called transition state structures, or the saddle point. And so the reason it's called a saddle point is because it looks like a saddle that you would use to ride a horse. For example, your legs would go down this way and that way, and then this would probably be to the front of the horse, and this would be to the back of the horse. And so the shape that's created here by this structure in the potential energy surface is called the saddle point. You'll notice that the saddle point is a maximum along this green curve. That is, as you go up the energy surface this way, you reach a maximum, and then it goes down this way. But then with respect to the other degree of freedom, the other way in which the molecule can move, you see that it's a minimum. And so that's true in general. The saddle point is going to be a maximum for one particular coordinate, and it will be a minimum for all other coordinates. These types of points are important because they directly connect a reactant to a product, for example. And so knowing the saddle point geometry or the transition state geometry and knowing its energy relative to the reactants and products is very useful information. And we'll probably touch on that a little bit more when we get to the unit on determining potential energy curves, where we'll look to calculate activation energies and so forth. For now, we just want to focus on locating these special structures, these so-called stationary points, the minima and the saddle point, using Gaussian. So let me introduce a concept from the molecular physics. It's a broad concept. It's also part of calculus in general. But in when you're dealing with this multidimensional function, you can define what's called the gradient, which is a vector of the first derivative of the function with respect to all of the degrees of freedom. So here for a molecule that has n atoms, and each atom has an x, y, and z component, the gradient would be a 3n dimensional vector of first derivatives with respect to the first derivatives of the energy with respect to all of the possible coordinates. And so here's a list of these different first derivatives. So this should have probably been atom 1, but anyway, the derivative of the energy with respect to the x coordinate of atom I, the derivative of the energy with respect to the y coordinate of atom I, and then you would have as many derivatives times 3 as you do atoms. Okay, so this would be a 3n dimensional vector, where each component is one of these derivatives. The physical interpretation of the gradient is that it's a vector that points in the direction at which the energy increases maximally. Okay, so it points to the maximum, like at a given point in space, it points in the direction of maximum increase. And so if you're trying to minimize the energy, you would essentially want to walk away from the gradient. You would want to go in a different direction, because if you follow the gradient, it's going to take you in the direction at which the energy maximally increases. You want to find the minimum, so you want to go in a different direction. And so that's the idea here. Gaussian is going to calculate these derivatives and then use them to find the minimum. From a physics perspective, the gradient is related to the force acting on the atoms. And so the force on the ith atom is just the vector of the components for that atom. So here we've got the derivative of the energy with respect to the atom's x, y, and z coordinates. The force acting on the atom is proportional to minus those quantities. And so quite literally, if you wanted to, you can use Gaussian to calculate the forces on the atoms at a particular geometry. In our application here, what we want to do is to minimize the force. And at the stationary points that we're trying to find, the force should be formally 0. That is, if you look at these minima, or even if you look at a maxima or at a saddle point, the derivative of the energy with respect to any direction will be 0. A related quantity from physics that has its roots in multidimensional calculus is called the Hessian. The Hessian, well, note that the gradient is a vector. The Hessian is a matrix. It's a 3n by 3n matrix of second derivatives. So this includes the second derivative with respect to x for an atom, the second derivative with respect to y for an atom, and all of the atoms plus all of the mixed partial derivatives as well. The Hessian is an important quantity in physics because it can be used to calculate, if we adopt a harmonic oscillator model, it can be used to calculate the harmonic oscillator force constants for the different vibrational modes of the molecule. Those are in turn related to the vibrational frequencies of the molecule. Another reason you might need to calculate the Hessian is because these force constants can be used, if you calculate the force constants, they can be used to improve the efficiency of the geometry optimization, so it can improve the performance of the algorithms that are used, make the calculation not necessarily go faster, but be more effective at finding the minima, the desired minima or maximum. As I said earlier, when you have a true minima, so that is when you are at one of these minimum energy geometries and you calculate the force constants, those force constants are related to the vibrational frequencies of the molecule, and we'll spend some time thinking about frequency calculations in the next unit. For our purposes here, the force constants and the vibrational frequencies are used to distinguish between finding a minimum and finding a transition state. And I'll show you the two rules that I'm referring to in a moment. But just keep in mind what Gaussian does, generally speaking, in its optimization and frequency calculations is it calculates the gradient of the energy with respect to the molecular geometry, and it also calculates the Hessian or the force constant matrix for the molecule. And so here's how the minimizations work in principle. It's not that complicated to understand what's happening, although the details of the algorithms are somewhat involved. But the idea is that you start with some initial geometry of your molecule that is not a minimum, and then you compute both the energy and the gradient of the energy at that geometry. Based upon that information, and possibly the force constants, you then determine a direction and size of a step that takes you away from that initial geometry. And the point is to take you from the geometry that you started with to a geometry that will have a lower energy. And then at that lower energy, then you'll calculate the energy and the gradient at that new geometry. You'll determine your next size or your next step that will lower the energy. And you just keep repeating that over and over again until the gradient or the force is acting on the atoms is zero. And at the minimum, if you found a true minimum and you do a frequency analysis, you'll find that there are zero imaginary frequencies. And by imaginary, I mean the imaginary number, the square root of -1. Let's see here. The criterion that Gaussian uses for determining whether or not a geometry optimization has converged involves four criterion. First, the maximum component of the force must be below a certain cutoff value, a very small value for the force. The root mean square of all of the forces on the atoms must also be below a certain tolerance. Okay, so not only is the maximum value of the force small, so must be the distribution of forces on the different atoms must also be small. The step that is calculated, so when Gaussian here determines what direction and size of a step for changing the geometry it will use, those steps must be below a certain cutoff. So the molecule shouldn't be changing too much. The algorithm should not be predicting the structure to change too much between steps. Likewise, the root mean square of the displacements of the atoms must also be below a certain tolerance. And those tolerance values, those cutoffs and tolerances, those can be controlled in the input file, although it's best to try to start with the default parameters because they've been chosen wisely. Nevertheless, it is often necessary to adjust these criteria when you're dealing with certain types of molecules, in particular so-called floppy molecules. These are molecules that are essentially very flexible. Oftentimes it'll involve a rotation about a carbon-carbon bond or something like that, where the energy simply just does not change very much. It has a broad and somewhat flat minimum into potential energy. This can sometimes cause problems with the default convergence criteria, and you may need to adjust them in order to improve your results. I'll just say a word here about transition states. So the other type of calculation that we'll look at in this unit is when you want to calculate the transition state connecting to minima. And so the transition state will be at a geometry that's a maximum along some reaction coordinate separating the reactants and products, but it'll be a minimum with respect to all other coordinates. And so there are, Gaussian has different algorithms for doing that. There's 3 to choose from. One of them, which I'm just going to call the TS method, is one where you need to you need to make a guess for what the geometry is of the transition state and hope that the algorithm will find the transition state from that geometry. Though if you started with a bad guess, then most likely Gaussian won't find the transition state. Another method, which is the recommended one, this QST2, this is where you start with optimized structures for the reactants and the products in your Gaussian calculation. So you have both the reactant and product present, and then Gaussian will take those 2 structures and then imagine for you what the transition state will be, and then it will proceed from that guess to find the transition state. That usually works pretty good. Sometimes it doesn't work, and you need to start with your own guess for the transition state using your chemical intuition. And here it's called the QST3. So you would provide 3 input geometries to Gaussian. You'd have the reactant and the product, and then you'd also have a transition state structure that you're suggesting. At the end of this transition state calculation, if you determine the vibrational frequencies for the transition state that was found, there should be 1 imaginary frequency in the calculation, and that indicates that you have a true transition state. And so I'm going to show you what I mean by that and how to find that in the output of your Gaussian calculations. But you always need to confirm whether or not you've truly found a minimum or whether you truly found a transition state before accepting the calculation as having worked. And so I'll show you what I mean. I wanted to make one more point about geometry optimizations. Suppose that this is your molecule's potential energy surface, and what you're really interested in here is the global minimum of the molecule. Well, if you start with an initial geometry that's over here, what's going to happen is Gaussian is probably not going to find that global minimum. It's probably going to just converge down to this local minimum. And so starting from any geometry that's over here on this side, Gaussian is going to have trouble finding the global minimum because it won't want to go over that energy barrier. It's going to find, the point I'm trying to make is that Gaussian finds the nearest local minimum. And normally what you need to do is you need to do a conformational search, meaning that you're going to start with a broad array of initial structures and then minimize each of those initial structures and see what minima come up. And then if you have a broad enough search in the sense that you've sampled some points over here and you've sampled some points over here, then you're likely to find all of the minima, and then by looking at the minimum energies for each of those minima, you can then determine which one's the global minimum and which ones are the local minimum. Okay, so it's you can't trust Gaussian to automatically find the global minimum for you, especially if you have a big molecule. You often have to do a series of calculations in order to find the global minimum. And fortunately, Gaussian has some relatively new tools that they've added to the software package to help us to do that. We'll go over that in a later video. So with that, I think I'm going to go ahead and stop this video here, and the next one we'll have some demonstration calculations for finding geometry optimizations and for finding transition states.